Hi everyone, welcome to Introduction to Machine Learning. This is lecture 11. In this lecture, we're talking about something known as bias-variance trade-off. This is an essential component of machine learning in general when we are building our models and then we are testing our models and assessing the accuracy of models. So this is important. And so in this lecture, we are not really looking at a new algorithm, but rather an important aspect of all models in general. And we'll keep talking about this topic throughout the course. And this is just the beginning, in which I talk about the bias-variance trade-off, the mathematical interpretation, and we'll also look at some graphical interpretations of this idea. Okay, so we'll talk about the meaning, why is it important, and how to deal with it. I would caution you that we won't go into the methods of dealing with it because there are many methods available, and the good news is that all the Python packages we are working with already come with the solution, right? So a lot of techniques like regularization and other methods that I'll talk about throughout in the course, but not as such go into a lot of detail about that. So essentially, I'll focus on the meaning and why is it important. Okay, some of the important trade-offs that generally exist in machine learning models are prediction accuracy versus interpretability. Now, why is this trade-off important? That's because if we're trying to achieve higher accuracy, we tend to go for more complex models. Now, we've looked at it before with linear versus the polynomial model, where we try to have a more flexible model, right? So in order to have greater accuracy. But the interpretation of those models, for example, the polynomial model with higher order terms, like let's say second order, third order, fourth order, and so on, makes it harder to interpret, to essentially understand the meaning of the coefficients, right? With linear models, it's easier. Another trade-off that exists is good fit versus overfit versus underfit, right? Just to give you an idea of what that means is, let's say this is what my data looks like. Okay, that's like really weird picture. This is my feature and this is my response. Like this is the outcome that I'm trying to predict, right? So model selection depends on a lot of factors. This, for example, in this is a linear model, and then this could be a quadratic order 2 model, and then this could be a very high order model that takes into account all the points of the training set, right? So which model to select? Again, depends on a lot of factors. So that's another trade-off that exists. And then simplicity versus black box. Whether we need to include, we saw that in the multinomial model, not really the multinomial, but the multiple regression model, where we were including many features. Obviously, this x is nothing but a vector of x1, x2, and so on. So what all features to include, right? And how many to include? Whether we should go for simplicity versus include everything, and then maybe we are not able to understand completely, but maybe we are able to reduce errors or able to achieve something else, and so on, right? So these are some of the important trade-offs in machine learning models, and then we look at them from different perspectives. But in this video, I'm focusing mainly on bias variance trade-off, right? So what is bias? Essentially, bias is an error, right? It is an error term, and I'll show you when I write the mathematical equation that it is part of the larger error that we've been measuring and that we've been trying to minimize, right? So the bias error is an error from the assumptions in the algorithm itself, right? How we modeled it and all of that. So if a model is said to have a high bias, that means that we've missed out certain relationships in the data, and then we have underfit. We have the problem of underfitting. So that's what bias means. Variance is an error from sensitivity to small fluctuations. So if you have a model that's like highly complex, right? It's trying to take into account all the training data into the mathematical expression that we are trying to derive, right? That essentially leads to overfitting, right? We are trying to include everything, and that leads to higher variance. Why? Because these models, they will try to adapt to the training set as much as possible, but essentially they do not generalize well when we try to fit the test set. And I'm going to show you 3 examples of what exactly this means. Okay, model error and its components. Let me write the general mathematical equation that we've been looking at, which is also known as the mean squared error, right? So in general, the expectation, and let us say the the fitted model is denoted by h of x, and I'm doing a hat to denote that this is the fitted model, right? And let us assume x of 0 and y of 0 is a test point, right? It's a point from the test data in which we will test our model, right? So what we do is we evaluate the model by checking the variability or the expected variability against the actual value. So essentially what we are trying to find out is the expected value of y0, right, minus what my fitted value calculated, right? With this, I will calculate the outcome, right, squared. So this is what we've been doing until now, right? Mean squared error is essentially this, and it has three important components, right? And I'll come back to this in some time, but just to let you know, it has a variance component which checks the variance of my fitted model. And this, by the way, has to be x of 0, right? Because I'm testing with the test point, right? So for all test data, essentially, plus bias, which is nothing but the difference actually with the fitted and the actual value. So that's what the bias is. And bias for that, and this is squared usually, plus the variance of this E, noise. This is the irreducible part. We cannot do anything about this part. So this is the mean squared error that we've been calculating. E is nothing but the expectation. So the expectation of the mean squared error is the variance plus the bias plus some noise. That's irreducible error, right? So this is the equation. This is the general equation. Now, after, before I go into the details of each of these terms, just remember that variance and bias both are part of the overall error, and our goal is to minimize that error. But how does that error comes out when we are dealing with training data versus test data? Let's look at those first and then come back to this equation, right? So I'm looking at three different data distributions. Now, why is this important? That's because different models are needed when we have different types of data. So let us assume, and I'm showing you a very simple, let's say one feature variable, and then this is the outcome variable. And let us assume this is the data, right? This is the data that I have, and I'm going to fit a linear model, and I'm naming it as 1, right? And then a quadratic model like polynomial degree 2, and I'm naming it 2. And then let's fit a higher degree polynomial such that takes into account everything, right? All the data points. And these points are, by the way, the training data, right? Because I'll obviously build my model on the training data, and I'm naming this higher degree polynomial as the third model, right? Now, flexibility means higher variance. And flexibility actually means that I'm trying to fit in everything. And as the order or as the complexity of my model increases, my flexibility increases. So I'm having a more flexible model here, right? So 3 is a more flexible model and 1 is a very rigid model. A linear model is a rigid model, right? So let's look at another graph which will use this information only and show me the mean squared error for this information. So let's say this is the mean squared error on the y-axis, and then let this be like 0.5 and then 1.0, 1.5 and so on, right? And then here I'm plotting the flexibility low to high, right? Now, if I use only training data to model this, right, what happens is that with let us assume 1 was my linear model, right? So let's say the error for that, and this is, by the way, only the training data. I'm not talking about test data yet, right? So it is a low flexibility model because we are just considering this ordinary least squares. We are not considering the other variability that's there. So it is low variability, obviously, and it is here, right? So mean squared error for this, if it is here, then as compared to this one, so this is my model 1, right? Model 2 will lie somewhere here. Flexibility is increasing, obviously, with the second model because I fitted a quadratic equation, right? So it took into account like more data points here, right? And similarly for the third one, as you can see, which is a very high order polynomial, right? It took into account all the data there, right? Mean squared error came down really like a lot here. This was for the training set. Now, what happens to the test set, right? Well, somewhat similar because test set will have new data, like new points, right? So let's say the new points are here, right? As you can see, these are the new points. These were the, let me cross them, right? So the cross ones will be the new one, and I'm going to test on these ones now, right? Now, as you can see, the linear model, although it will miss out some points, but it will encompass some of them, right? So it will again have low flexibility, model 1. But however, it's going to be somewhere here. The quadratic one took into account like a lot of training points, right, from the training data itself, and it came somewhere here, right? So the mean squared error comes down for this one as well. But what happens to this overfitted model? This overfitted model really took into account each and every point in the training set, right? And so obviously their chances are high that it is going to miss out every point from the test set, right? Which will lead to higher mean squared error, right? So although the flexibility of the model has increased, and by the way, this is test set, right? So this is how my error will begin to rise again, although the flexibility of the model is high, but I've overfitted it. So it did not generalize well with the test set. Although with the training set, the error came down, but this wasn't true for the test set. Okay, let me look at another sort of data which is more well-behaved, which by well-behaved, I mean like this. So this is my data. So this is model 1, just like before, model 2, and then our model 3 overfitted one, right? Again, when I look at the mean squared error for the test and the training set, again, let's say this is 1, and then this is 0.5, and this is 1.5, right? Again, for model 1, in this case, because the data is really well behaved, and then this is flexibility, right? The data is really well behaved. For the training set, it always comes down, no matter what you do. It will come down because it will learn well from the data, right? However, with the test set, this might go up slower, but it will still go up. Although this is well-behaved data, right? So we are expecting a lower error. But as you can see with the test set, again, this model that takes into account this, that overfits, does not generalize well. And one last example with a very bad behaved like data. Okay, these are weird data points, right? If I try to fit a linear model and then second order and then an overfitted that tries to take into account everything, right? So this is again 1 and then 2 and then 3. Again, we'll see a similar trend, although not exactly like this, which means even the lower flexibility model here will show higher error given that the data is not well behaved, right? So even with the test and the training, however, we'll see this kind of a curve. We'll see that with model number 2, it comes down, and then with higher flexibility, it begins to rise, right? So in this situation, although the linear model is not doing well, this is the test set. So with the training, again, it goes down. No matter what, it goes down, whether it's this is 1, this is 2, and this is 3. Third model, but even with a test set, so here we can make a selection of like maybe this model is better than this or this is better than that. So it really depends on the type of data we are dealing with, right? And why is that? So that goes back to our math equation that we built earlier that said that the mean squared error actually has variance plus bias squared plus the irreducible error, right? Irreducible error. Now we cannot do anything about it. This is the general noise that exists there. This variance, which was defined to be variance on the fitted model when we were testing it with the test point, which was x0, right? This is due to overfitting, right? This is due to training sets because we have overfitted the model in the training data, and so it's not generalizing well. This bias squared here is nothing, but because over different training sets, this is actually calculating the expected value of the fitted model minus the actual or the true value, right? So it's calculating that difference, the difference between the fitted expected value over all the entire training set minus the actual value that's there in the test set, right? So therefore, as flexibility increases, when we saw in the previous graphs, variance increases and bias decreases, right? Therefore, choosing flexibility based on average test error results in bias variance trade-off. What does that mean? Now, if I'm going to bring my first, which wasn't my first data set, which wasn't like very well behaved, but which wasn't like really weird, but somewhere in between. And if I try to plot mean squared error and bias, and this is flexibility, by the way, against flexibility and bias. So this is how bias will look like. Bias tends to decrease when flexibility increases, but as flexibility increases, as I tend to overfit, my variance will increase. And this trade-off exists, and essentially we as model builders are trying to find out this point, because this bias plus variance leads to this mean squared error curve. We saw that here. That's what the equation tells us, right? And so we are essentially trying to find the model that lies somewhere here, right? And again, this picture can be different for a well-behaved model. So I would maybe guess that a well-behaved model would have a mean squared error like this. So maybe you're looking at a point somewhere here where just the variance is increasing and maybe bias is not changing as much, right? For different models. And similarly, for a very bad behaved data set, the one that we looked in the end, we might have a mean squared error curve, something like this, and bias also reduces and variance maybe not increases that much, right? So again, depending on the type of data we are dealing with, we have to figure out what model lies here, because we are dealing essentially overall with this bias variance trade-off, and that's what actually forms the mean squared error. Right? So with this, I end this video, idea being that we as data scientists are supposed to come up with models that somehow take us to this point, somehow reach to this point, right? And we'll talk about methods that actually help us do that, right? So we'll talk about that later on in the course. Thank you.